year was Jack's best trip ever.
Fuck you, Jack.
Jack's ruining my day. Hi. I wrote this program like a week ago to test, like, I gotta remember how it all works. Okay, so that's x-axis, y-axis. Page down. Can I go y? No. Z. X. Y. Alright. Not ready to start yet, obviously. T. 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 Alright, T works. Up moves. Oh, this is the weight. Oh. Oh. We can adjust the weight, and then there's a normalized weight. Alright, can I draw the weighted vector? It's fucking math time. By the way, if you're learning math from a guy who literally failed out of high school math, so good luck. Look at that, some fucking blended rotations and shit. Isn't that nice? How the hell did we do that? Alright. I'm gonna let people sort of trickle in for a little bit. Am I randomly freezing? Is it me? Oh. OBS says I haven't dropped any frames. I got a lot of stream lag though. I have my stream open as well. I gotta remember the top inch of my screen, or top 120 pixels of my screen is cut off. Or I guess 110 or so. Alright. I'm gonna chill for a bit, let people come in. Oh, man. I bought a tablet. Like a Wacom thingy. It's fucking garbage. Randomly disconnects. If it randomly disconnects once during the stream, I'm going to return it. Trying out Mischief too. I tried a bunch of other ones because I didn't want to buy one because I'm never going to use it for anything but this. But turns out they're all really awful. Fuck. Oh, you guys got to deal with my writing. Haha, you're fucked. I hope you didn't plan on learning anything, because you ain't learning shit with my writing. This is about as good as I can write. And I fuck up a lot with a tablet. More so than with pen plus paper. You'll notice that it just suddenly got slanted, like it started. At least we can change colors here. I was watching Khan Academy to see how he did it. So we started like pretty horizontal, and then like 5 lines down, we're at like a 30-degree angle. We're fucked. You might want to skip on the tablet text. I can't. I gotta do tablet text. It's kind of the whole thing is gonna be a tablet. Don't worry. I'll work slowly. All right. Indecipherable hieroglyphic language. Yeah, it's pretty bad. I'm sorry. Let's see. How good can I? That's a 1. Alright, that's not so bad, right? You guys can read that, right? Might help to make the brush thicker. We can try that. Is this easier to read? How good can you wank? Wank. Real good. Alright, well, this is just how we're gonna have to do here. Oh good, you can read it. Okay, good. Good. Writing is not my forte. Okay, that's why I type. So I'm still gonna wait another probably 5 minutes. I'm gonna finish my coffee and my little cubes of cheddar. If anybody has any questions or wants to talk about something, just ask me now. During the stream, feel free to interrupt, because like just at me at SSS McGrath or whatever in the chat, and just be like, hey, asshole, you did something wrong, or hey, I don't understand something. Because I'm going to try to do my best here to try to get people to understand, or to try to help people understand this. Because I remember when I learned this shit like 10, 15 years ago, I guess it would have been 02 maybe. I had a really difficult time like wrapping my head around it. Because, well, I'll talk about it in 5 minutes when we give time for everybody to come. So I started working on the game again. It's people who watch the programming part of the stream. It's pretty cool. I made an infinite loop. Check this shit out. My game. Yeah, so... Wait, is that a black hole? No, it's a black hole. Right, so we can make these portal things, and like if we shoot into one portal, it'll come out the other. It's like Portal, like the game Portal. Oh fuck, the black hole is taking... The mass of the black hole is taking too much precedence. Hold on. So like, we can have this shit, and I can be like, yeah. Pew! And it comes out the other end. Wait, what? Oh no, I broke collision earlier. Alright, that's the last thing I did on the stream today, was break everything, so I can't even show you the cool infinite loops. That'll be the first thing I fix tomorrow. So if you want to see me fix collision, I'm debating actually whether I want to do like the whole, like do a big broad face collision thing, or if I just want to get hacky collision in working. I probably just want to do something hacky. Just because, you know, it's a little easier. I guess I should tweet about this, right? Streaming some shit about some shit. Streaming, an introduction to Quaternions in 1 minute or so. No, I haven't decided on the business model. It's kind of unimportant. I guess the least important thing. The most important thing is having a good game. Figuring out how I want to try to survive is like secondary. First thing I'm concerned about is making a good game. We're probably going to take donations. What do you mean about the intro? We're going to take donations and stuff. So, hopefully I can make a little bit of money off the Twitch streaming. Once the game is, like, playable, I think it'll do kind of okay. And we'll see how that goes. I also have another idea for... for streaming that I think people will really like. Like, if I'm really desperate, I think I have a good idea. Or I'll just go get a contract job for a little while, and part-time contract job, and that'll make enough money to do. To pay for the game. Yeah, I am torn. I mean, I'm not really torn. I think just because free-to-play has never been done ethically doesn't mean it can't be. And the amount of good that you get from free-to-play, like if you're playing a competitive game and you press find match, you don't want to wait around for 4 hours to find a match because there's only 500 people playing, right? You want 100,000 people playing so that when you press find match, you find the match instantly, right? Like, that's worth so much money to players, and that makes the game so much better, that Casey's argument of one player subsidizing other players, yeah, they are subsidizing, but you're getting something out of it. You're getting people to play with. And, you know, for some people that might be worth a $30 model of your favorite character every couple of months or something like that. Maybe you do spend $200 a year on it, but you get, hopefully, something good out of it. We're not trying to be Star Citizen where we're taking your money and on grandiose promises of not delivering anything. You can watch the game get made in real time and see how that, see how that works. So you know that we're not taking your money and buying $200,000 Porsches with it. Like some unnamed person who makes a game about spaceships and hasn't delivered any spaceships. How much money have those motherfuckers made anyway? I love this. All they talk about. Where do they? News. Wait. Store. Let's see. Dude, I can buy a starter. Man, I can buy this ship here. That's a nice looking JPEG. How much does the JPEG cost? How much was it? Buying options. Oh, wow. Are they going to upsell me? Yeah. I want to buy this thing. How much is this thing? How much does this JPEG cost? $155. It's like $1 million Canadian right now. Fantastic. $105 million in Star Citizen. Yeah. Well. Sad. I mean, I don't care if they make $105 million. I mean, that's good for them. But, like, actually deliver something would be nice. If they delivered something, I'd have no problem with the game. But, like, what they've delivered is not even, like, it's just not right. It's not right what they're doing. Call to action. Gary Oldman. How much money do they pay for Gary Oldman? Pre-order, yeah. Do I have to buy this game separately? Like, do I have to buy the single-player part separately? What a fucking scam these guys are. Alright, enough about them. Let's talk about math. So I have a little bit of notes here. Alright, so first thing you need to know, I know shit about math. I failed out of high school. I didn't do any math classes in high school. I took no math in post-secondary. I didn't go to post-secondary school. I don't know anything. Okay? So, take everything I say with a grain of salt. But, I've been doing this for a long time. And programming games, that is, for a long time. 3D games, 2D games, whatever. And I've sort of picked up a intuitive understanding of a lot of math concepts that I think will be useful for other people. Like I don't really understand. Like I went to the Wikipedia page of Quaternions. Like I went here, right? And I'm like, okay, let's see, because basically how this started was I was like, hey, I posted on Twitter. I was like, hey, maybe I'll teach some people some math, because I remember having a lot of trouble before. When I was younger, I had a lot of trouble learning. When I was really young, I had a lot of trouble learning math, and lately, lately I'm having trouble again. But there was a good 10-year period where I was learning math concepts pretty quickly, pretty regularly. And I didn't really have any trouble with them. Quaternions was about the time when I started getting good at learning math. Anyways, so I was like, yeah, if anybody wants me to teach math from like a game programmer perspective, I can do that. So what do you guys want to learn? And fucking half the people, like I got like 20 people who were like, I want to learn Quaternions. And I was like, all right, I can teach Quaternions. So the first thing I did is I looked up how other people taught Quaternions. And I've come to the conclusion that no one who's teaching an intro, like an introduction, no one who's doing an introduction thing on the internet about Quaternions understands Quaternions at all. There are high-level things on the internet that written by people who clearly do know what they're talking about, but all of the introduction stuff was just awful, like Stack Exchange and all of that stuff that people on Stack Exchange linked. It's just bad, right? So there's clearly a lack of a good sort of instruction on how to get an intuitive understanding of how you use Quaternions in programming to represent 3D rotations, right? Like I don't think there's a good example of it, right? So I'm like, this is a perfect topic to teach because there isn't a good example. So I wrote up what I wanted to talk about, and I sent it over to Casey, who is like in my opinion, was at one point the expert on Quaternions, and he's like, hey, you missed these things, exponential mapping and double cover, which is a big thing he wanted to talk about. And I was like, okay, I'll cover double cover. I'm not going to, because he did such a good job that there's no reason to do double cover, I don't think. I'll link you his explanation of double cover. I'll talk about what it is at the very end, but I'll link his explanation of it, because I don't think I have anything to add to that. And exponent mapping, I'm not doing that because I don't understand it, and I didn't really... I was going to learn it, but I was like, no, it's better to keep this to an introduction, because I want to keep this to like an hour. Maybe an hour and a little bit. I don't want this to go too long. So I don't want to cover crazy in-depth topics. If you want to learn crazy in-depth topics, tweet at me and I'll do it. But I think the next thing... So a lot of people ask for vector calculus and linear algebra lessons, so I'll probably do those next. Maybe I'll do an advanced Quaternion thing if there's a demand for it, but I think Casey's lecture on double cover sort of covers that quite well. So most of the stuff you read about Quaternions on the internet is this garbage, which doesn't make sense to humans. I mean, if you understand formal math or whatever, this is probably quite straightforward, but it's not straightforward to me at all. So I'm going to pretend that I didn't see that. All right. So, Quaternions. What the fuck are they? Quaternions are just vectors with 4 components. Their magnitude is 1. That's all they are, really. Quite simple. So, first we're going to talk about rotation in 2D, right? And why do we even need Quaternions, right? Like if you take a look at a 2D rotation, right? So these are my axes. I'm gonna, there we go, look at that, straight. I'm gonna call them X and Y, but that's not a, when you're trying to think about this, you don't want to think in terms of X and Y, but that's fine. For our case, it's fine. Right? So, we have a vector, we have a rotation that goes, in this direction, and the common symbol that we use is theta, a Greek symbol theta. And that means a rotation by some amount in this direction, right? Like this is a 90-degree rotation, or pi over 2 radians. It's a 180-degree rotation, or pi radians. Or this is a 270-degree rotation, or 3 pi radians, and this is a 360-degree rotation, or 2 pi radians, right? So this is sort of how you represent rotations in 2 dimensions, right? And you'll notice that there is one number. Khan Academy uses lots of colors, so let's do the same. Look at that shit. Fuck yeah. So, rotations in 1 dimension, or 2 dimensions rather, is just theta, right? And once you have the theta, you're representing your all the rotation that you could possibly want in 2 dimensions, right? And you're set, you're good to go. 3 dimensions is a little bit trickier, right? So 3 dimensions, there's lots of ways to represent rotations. I'm not going to go through all of them, but if you take a look at the first way, which I'll talk about very, very briefly, I'll use X, Y, and Z again, because that's what you're supposed to do or something. So the first method that you'll probably ever read about is something called Euler angles. And Euler angles are just a rotation around X, a rotation around Y, and a rotation around Z, right? These are not an rotation around Z. Wait, is that right? Who cares? This is a way you can represent rotations. So you can imagine if you have an object here, and can we see it? And you want to rotate it around, your vertical axis. You can rotate it, a little bit, and then you want to rotate around your horizontal axis or whatever, and you can rotate it. And that's a way of representing rotations. There's a couple of problems with them. There's a lot of problems with them, right? But the first problem is you can't interpolate. Bad for interpolation. And another bad thing about them, the other one that everyone cites as being bad, is a thing called gimbal lock, which really isn't that big of a deal. Like, people think it's a huge deal, but it's kind of not. It's basically when you rotate one axis so much that it lines up perpendicular to another axis, and you lose a degree of freedom in your rotation. Like, this is because you're a 3 degree of freedom rotation, but if you rotate such that your X and your Y axis line up with each other, there's no way to re-separate those axes, and you lose a degree of freedom, right? You're basically losing a basis vector of rotation. It's not that big of a problem in practice unless you're making like a flight sim or something. But anyways, the fact that you can't interpolate them easily is a really big problem. So the new fad that has been around since probably the early 90s, I think Tomb Raider, the first Tomb Raider, is the first time I remember hearing about quaternions. Maybe they were used before that, probably, but the first time I ever heard about them was from the very first Tomb Raider game on the PlayStation 1. And quaternions are just a way to represent a rotation in 3D in the same way that we use just the number theta in 2D. In 3D, we'll get our axes back, right? So we call this one Y, and we call this one X, and we call this one Z, right? So what normally, how a way you can think about a rotation in 3D, right, is an axis about which you're rotating, right? So imagine I went over to here, that's some amount on X, some amount on Z, and then I go, some amount on Y, right? And I have this vector here, and it's made of sort of those components, right? And actually, it would be like that, I guess. Let's clear up that. All right. Anyways, so you'd say I want to rotate about this axis by some amount, right? So if we even go back and we look at our 2D where we had just an X and a Y, we could say in 3D that there's an X axis that's coming straight out at us. Is it right-hand rule or left-hand rule? I don't remember. I don't know. The Z axis is going straight away from us, actually, not straight at us. I never remember these things. So the X axis is the Z axis rather. Z axis is going straight out from us, and we can rotate about that, right? That's the same. That's like moving a two-dimensional rotation into 3D, right? Because if you think about it, if you have a square like this, right, and it exists in this axis here, and we rotate it by say 45 degrees, you get like this or whatever. That's if this is a 2D rotation of theta is equal to 45 degrees, that's really the same thing as a 3D rotation about the z-axis, right? So 3D, basically, we want to think about rotations in terms of an axis about which you're rotating, and and an angle about which you're rotating, right? So your axis exists in 3 dimensions, obviously, right? So you have an axis 0, 1, and axis 2. So you're rotating about this axis, and you're rotating by theta, right? And you'll notice that this is there are 4 components, right? And if you put this into you make a vector out of this, you have a 4-dimensional vector, right? So, we can even look at, I wrote this little test program here. So let's look at the little test program. Let me just hide the Quaternion interpolation. So if we look at our little test program here, you can see, if you look at this pink, this pink one here, that's a rotation about the x-axis, right? So I can actually rotate this around, and you can see it being rotated about what would be called the x-axis normally, right? I can move the rotation by about y. I can, move the sphere about which we're rotating. So, we can rotate about anything we want, and then rotate by t. But you can see that there are 3 points that are moving, right, at all times. Or there are 3 dimensions. There are rather 4 dimensions in which this are moving, right? The axis is moving, so I can move it by amount on the z-axis, I can move it an amount on the y-axis, and I can move it an amount on the x-axis, and I can also change its rotation around that axis, right? So there are four components which make up the rotation, right? And that's where quaternions sort of come from, right? There are 4 component vector. Now, what's interesting about quaternions is we deal with unit quaternions, which means their length are 1, right? So all quaternions have a length 1. If you think about a 2-dimensional vector, right? So if we have a 2-dimensional vector with length 1, right? So here's a 2-dimensional vector with length 1, here's a 2-dimensional vector with length 1, here's a 2-dimensional vector with length 1. And if we graph all the 2-dimensional vectors with length 1, you'll get a circle, right? In 3D, if you graph all the 3-dimensional vectors with length 1, they'll all lie, well, whatever. They'll all lie on a point on a sphere, right? And this is useful because, like, let's say, don't even know how that happened. Let's say that we're trying to interpolate something, right? If we're trying to interpolate around the outside of a circle, that's reasonably easy to do. If we're trying to interpolate around the outside of a sphere, that's again reasonably easy to do, right? So what we want to do, an interesting thing about these things in 4D, if they're length 1, then all of their points exist on the outside of a hypersphere, like a I call them 4-dimensional circles because I don't see why we have to come up with names for things, but they're called hyperspheres. It's just a 4-dimensional circle. It just means that any point on the 4-dimensional circle is 1 length from the origin, basically, right? So we can set up our quaternion in any way, or we can set up a 4-dimensional. There are an infinite number of ways we can set up a 4-dimensional vector from an axis, from a 3-dimensional axis, a1, a2, and a theta. So we could set this up in infinite number of ways to get a 4-dimensional vector. That's length 1, right? We could just do whatever we want and then normalize it, right? So we could do 3a0, a2 squared, a1 times pi, theta e to the theta, right? Like we could do this, right? And then we could just normalize it, right? Is that the symbol for normalize, or is it 1? I don't know. I think it's 1. I think that means magnitude, and that means unit. I don't know. There. So we could do that, and then we have ourselves a 4D vector that lies on a hypersphere, right? That's fine. You could do that. You could do anything you want. You could turn your 4 components. You could just go A0, A1, A2, theta, normalize that, and you're a point on a hypersphere, right? Or a 4-dimensional circle. But that doesn't get you anything, right? All it does is it puts you somewhere randomly on a 4-dimensional circle. It doesn't put you into any sort of coherent space, right? So the beauty of quaternions is they put you into a coherent space on a 4-dimensional circle. So the formula for a quaternion is I'll write it with x notation, right? So it's ax sine theta over 2. So quaternion is ax sine theta over 2, ay sine theta over 2, az sine theta over 2, and then cosine theta over 2. Normalization, yeah. Okay, well, that little hat should mean like unit vector, if I remember correctly, but maybe I'm wrong. I don't know. Me and formal math notation do not get along. So this is the actual formula for a quaternion, right? So it takes your axis, and I'm just going to simplify it by just saying axis of rotation sine theta over 2, cosine theta over 2. Right, so this is 3 parts here. So this is how you construct a quaternion. Now the beautiful thing about what this gives you is this gives you, as long as your theta is in the range of 0 to 720 or 0 to 4 pi. As long as your theta is within this range, so 2 full turns equals 1 turn around the circumference of the hypersphere, what that means is that every single quaternion maps uniquely to a point on the hypersphere, and every point on the hypersphere is completely covered, right? So every single axis that you can think of, normalized axis that you can think of, and every single angle between 0 and 2 full rotation, 720 degrees, gives you a unique point on the hypersphere. That's... Alright, I have just defined that hat. So if I do this, that's a vector. If I do this, that's a unit vector. Unit vector. Unit vector is just the length of it is equal to 1. Okay. So, yeah. Alright, so basically, yes, what the quaternion does is it takes every single axis and angle that exists in 3 dimensions and maps it uniquely onto a point in 4 dimensions that lives on the edge of a circle. And what that gives us, edge of a 4-dimensional circle, or hypersphere as they call them. So what that gives us is a really great way in which we can interpolate between different rotations, right? So if I have a rotation around, let's just make it simple, right? So if I have one rotation that's around, the x-axis, a rotation of 90 degrees, and I have another rotation around the y-axis of 35 degrees, for example. This will map to some quaternion. This will map to some quaternion. So we'll call this Q0 and Q1. And we can very conveniently interpolate between those 2 rotations along the circumference of the hypersphere, right? And that's fantastic, right? This allows us to have a rotation, like let's say we're playing a flight sim game and I'm looking this way, but I want to look over here. That gives us a very smooth path, which we can both, rotate the ship and the direction that we're looking in one sort of smooth arc, right? Another thing that it does that's really important for character animation is it allows us to blend n quaternions, right? We can take, let's say I have a joint, an animation where my hand is down and then I'm moving my hand up, or like something more complicated. My hand is down and I'm moving my hand to point a gun, because guns are what we do in video games. But in the meantime, like my arm moves back a little bit or something like that, and in that there's like 5 or 6 keyframes that exist, and you sort of interpolate blend between that whole like track of animation poses. There might be 10 quaternions that you're interpolating between, and that's 10 different that's 10 different rotations that exist per joint, and you can interpolate between all 10 of those in one go, because all 10 of those points you're able to, all 10 of those quaternions or all 10 of those rotations you're able to map to points on a hypersphere and then just linearly blend between them. And it's like it solves every single problem with 3D rotation that I've ever encountered are solved with quaternions. There are problems that I haven't had to deal with that quaternions do not solve eloquently. So, if you've ever taken a flight, this was sort of the most pronounced time that this has ever happened to me, is I was on a flight from Toronto to Frankfurt, and I should actually ask, does this all make sense? Have I explained this well? Have I explained it like how I have like a sort of an intuition for this? Because I feel like all of the instructions that I've ever read about quaternions, like all of the introductory topics that I've ever read about quaternions on the internet, didn't explain any of the shit that I just explained, and this is sort of like what's really important about them. Does anybody have any questions, or does everything make sense so far? I know there's quite a big stream delay actually, so I'm gonna wait for this. 2 full rotations. Okay, mathematically, I have absolutely no idea why. I don't. I mean, like, other than the obvious fact that the quaternion is a sine theta over 2, cosine theta over 2. Other than like the fact that these 2's are here, that's as far as the why it's 2 dimensions that I understand, or why it's 2 full rotations that I understand. There is a physical reason why. Tau is stupid, and tau is stupid because in the real world, at the quantum mechanical level at least, and I can show you, I wasn't going to do this, but I'm going to do this. Taking off my belt. Okay. I'm going to try to do this. Paul Dirac. There's this guy, Paul Dirac. He's a particle physicist. Came up with all sorts of shit. Signal processing stuff. Some cool shit. You do not get 2 angles that give the same value with quaternions. And there's a thing called double cover, and I'm not going to explain it much. I'll link you to Casey's explanation, because I believe he's the first person to ever do it. So I'm going to teach you the belt trick. I think Elephant knows the belt trick. So Paul Dirac had this belt trick, and basically what he used it to do is prove that in the physical real world, there is a distinction between a 360-degree rotation and a 720-degree rotation. When you look at particle physics and you look at the spin of... No, I'm not doing a Mobius strip. When you look at the spin of electrons, you can have, or spin of fundamental particles, I think an electron has a half spin. Anyways, so you're talking about the orientation of particles as though there were strings attached to the end of them, and there is a difference in the real physical world between a 360-degree rotation and a 720-degree rotation. So, no, I'm saying that 1 full rotation is 4 pi and 2 tau. That's why I think tau is stupid, because rotations are actually 720 degrees in the physical world. We're just too stupid to see it. So if you take this belt, can you see the belt? Okay, you can see. So if you take this belt, and I'm going to twist it twice. I'll demonstrate here so you can actually see. So I'm doing 1. Okay, I've just done a 360-degree rotation of the belt. Okay, so I've taken one end and I've twisted it 360 degrees, right? And I'm going to take it, see if I do this right, and I'm going to put it under the side, and you'll notice that the belt is still twisted. Okay? So the belt is still twisted after doing 360 degrees of rotation. So I'm going to take this, and I'm going to do the exact same thing. So that's 180. That is 360. That's 540, and that's 720 degrees. I've now done 2 full rotations of the belt. I'm going to do the exact same procedure where I just take it, and I stick it under the other end, and I pull it straight, and the belt is no longer twisted. Definitive proof that in the physical world, there is this distinction between 360-degree rotations and 720-degree rotations. When you get into particle physics and you get down to the really sort of small, even like theoretical particles that we aren't sure exist or whatever, they're all defined in terms of 2 full rotations is different from 1 full rotation. If that's why that mapping to to 3 to 2 full rotations is why Quaternions are like that, then that's fucking cool. But I don't actually know. Yes, you can do it by rotating something in your hand, but my shoulder doesn't move that way. I've seen videos of it, though. It's pretty cool. Quick question. Do I have to worry about losing information moving back into 3 dimensions? No, because you're never moving back into 3 dimensions, right? We're not taking... Like, this was the thing that I think people who are teaching Quaternions don't quite understand, otherwise they would explain it. And hopefully I can explain it to you. So if I can't, keep asking me, because I'll do my best. You're not taking a 3-dimensional point, right? Like the rotation, it's just like in 2D, right? In 2D you had a theta. Let me see if I can draw this a little bit nicer. Right? In 2 dimensions you had just an angle, right? You had a theta angle of rotation, right? That's not a point, right? That isn't intrinsically a point. I mean, you can do e to the... Ignoring Euler's formula, this isn't a point, right? This is just a rotation, right? It doesn't mean a physical point, right? If you were to construct a vector out of this, like if you were to go cosine theta x plus sine theta y, for example, then you've taken your point, you've taken your rotation, which is not a point, and you've turned it into a point, right? So this is taking theta of a rotation defined as a single number theta into a point. This is a 2D vector. This is how you do this. But if you're just talking about the rotation itself, like the actual representation, the mathematical representation of the rotation, it's just a point, right? Quaternions are the 3D equivalent of just this point, right? So in 2D, you need just the theta. In 3D, you need an axis and a theta. So when you move it, an axis, a 3D axis plus a theta this is represented with 1 number, right? This is represented with 4 numbers. So you're never actually going from 2 dimensions, or from 3 dimensions to 4 dimensions. Your rotation is always a 4-part vector, right? It's always your rotation about x, y, and z, and then a rotation, or it's always an axis defined in x, y, and z, and then a rotation around it, right? It's never a point in 3 dimensions, right? So when we're doing any operations on these quaternions, we're doing it, we turn our 4 numbers that are required to do the operations, our 3 axes and 4 numbers, we turn that into a vector that just happens to nicely map onto a 4-dimensional circle or a hypersphere. Does that make sense? Yeah, it's just axis plus angle. Is that clear? I feel like that's probably the thing that's missing from most explanations on quaternions. Okay, are we clear up to this point? Is everybody happy? Does everybody like this? Are we all happy? Do we understand that the quaternion is just the 2D equivalent of just a theta? Alright, cool. So, let's switch colors here just for fun, because I want to be conned so badly. Alright. I'm going to talk about handmade HMH bots here. All right then. So I'm going to talk about great arcs now. So when I was flying, I was going to get to the story where I was flying from Toronto to Frankfurt, and on the airline that I was on, you had a screen on your TV, you had a TV right in front of you, and there was a map button, and you could see the map, and the map basically drew the flight path for the plane and where we were, right? And at one point, my wife looked at it, and we were almost up to Iceland, right? According to this, okay, Jesus, I have to stop reading the chat. We were on a point, and it looked like we were just about to the point of Iceland, right? And that's crazy because Toronto and Frankfurt are quite a bit further south than Iceland. So why were we up so high, right? Well, one of the reasons was when you project a globe, it's all fuckery, and you don't actually go that high. But another reason, or it's the same reason, is that when you take a globe and you project it flat, what you think is a straight line, like it looks like a straight line between 2 points, that's not actually the straightest line around a circle, right? So if you take a sphere, which I should have actually brought a ball. You know what I'm going to do? I'm going to go get a ball, because this will help. I'll be right back. Okay, sorry. I guess that was on. All right. Yeah, I know. I just muted myself. Are we good now? Yeah, I know. Are we good now? Are we all right? We happy? Can you hear me? Hello? I assume that everybody can hear me. Continue. Okay, we're Gucci. Okay. All right. So when you look at a point on a sphere, right? Let's say I'm going between. Can we see? Can we? There's one point. Where's the other? Oh my God! I'm trying to do it backwards in a mirror. Holy shit! Life's hard. Okay. So yeah. Anyways, 2 points, and if we go connect the dots, we're traveling along this sphere, right? This arc, or this line, the shortest distance between 2 points along the surface of a sphere, is called a great arc. And great arcs have a few interesting properties. The first interesting property is they are coplanar, as any two vectors would be, or all the points lie on a plane, right? So if you take the sphere and you get to the very center of the sphere and you were to create a vector that goes from the very center of the sphere out from one point and then out to the other point, you will define a plane with those two vectors, and that plane, imagine a sheet of paper here that goes through the center, slices right through here, and then connects this point to this point. All the points of that great circle, of that great arc, lie on the projected 2D vector, if that makes sense, right? Or the projected 2D plane, right? So This is a plane. It's an infinite plane, as you can tell from its finiteness. This infinite plane, if it went through the sphere that's very solid and can't be cut, and connected each point of this through the great arc, that would be constructed with two vectors. Let me see if I can draw it here, right? So we have our circle. We have 1 point here, 1 point here. This is the center of the circle. We construct a vector here, and we construct a vector here, v0 and v1. As you can see, this vector is particularly straight. These define a plane, as any two vectors that are not collinear define a plane, and that plane exists through the sphere, connecting these 2 points, the 2 points that we want to go between, and all the points of the great circle or great arc that connect these 2 points along the outside. So if you can imagine that, and this is a sphere, and this is the origin. This plane that's defined by these two vectors, all the points of the great arc that connect v1 and v0 through the minimal path along the outside of the circle, called the great arc, that great arc there, all those points will lie exactly on that plane defined by those two vectors. Does that make sense? Are we happy about that? Does that make sense? I'm going to assume that that makes sense, because I'm going to talk a little bit more about that. Now, what you've learned about vectors, hopefully, is that any two vectors that are non-collinear define a plane, right? So as long as they're linearly independent, as in if one vector is here and the other vector lies directly on top of it, if this is v0 and v1, these two are obviously collinear, they don't define a plane. Literally any other two vectors define a plane, right? So we know that these two define a plane. The cool thing about any n-dimensional sphere, whether it's 4-dimensional, 3-dimensional, 7-dimensional... Okay, sorry, hold on. I don't actually know if this works for n-dimensional, but I know it works in 3, 4, and 7. And we only care about 3 and 4. So we know it works in 3 and 4. I believe it works in everything, but I'm not a mathematician and didn't prove it. But 3, 4, and 7, it works, right? Did Levi sponsor Elite Dangerous? What? What the fuck are you talking about? What the fuck are you talking about? I don't know what the fuck this guy's talking about. Shut the fuck up. Okay, so what is 7-dimensional? It doesn't matter. Like, this should work for any dimensions, right? But we're concerned with 7 and 4 dimensions. So anyways, the point is that even on the outside of a hypersphere, the shortest point along the outside of a hypersphere it still lies on a plane, right? And we can define that plane simply by two quaternions, because quaternions, remember, are 4D vectors, right? So if a quaternion is a 4D vector, and there's two quaternions that are not collinear, we know that defines a plane, right? It doesn't matter how many dimensions this is, right? You can have a vector with 36 dimensions. If you have two of them, it still defines a plane, right? There's still one plane that is defined by those two vectors, right? So if we have two planes that are, or two quaternions that are, two quaternions that exist that are not collinear, they define a plane, and the shortest distance between those two quaternions on the outside of the hypersphere is exactly lie exactly on the plane, just like I showed in this example with 3 dimensions in this thing, right? It's the exact same thing, right? Does that make sense to everybody? This example here, plane going through 3-dimensional sphere. If you take this plane and you go through a 4-dimensional sphere, I can't show you that. I have no idea what that looks like. It doesn't matter. The point is that the math for 3 dimensions and 4 dimensions are the exact same, right? So if we take a plane and we slice the sphere along 2 quaternions, then we have a plane that all points along the great arc between those two quaternions will lie on, right? So, if we're happy with that, then I can explain to you what slurp is, because that's all slurp is. You have probably heard of slurp, because I think there's a slurp button in Unity. And so since there's a slurp button in Unity, everybody uses slurp. So let's talk about slurp, because I just explained it. Slurp is a function that takes two quaternions, Q0, Q1, and a t value, where t is between 0 and 1. And all it does is it basically walks along the outside of a hypersphere exactly in the same way that we do in 3D. You have to imagine this is 4D, which you can't do because no one can. I don't think. Maybe some people can. I don't know. But anyway, so if this was a 4D circle, imagine walking along the outside of a 4D circle. The path that that 4D circle takes is defined to be on a plane because there's only two things that you're going between, right? So we can just create slurp. That's not particularly hard, right? So if we were to draw our coordinate system now, and instead of x and y, let's call this basis axis, let's just call this Q0. Okay, so this is our first quaternion, right? And now, you know, maybe here, this is quaternion 1, for example, right? And we can get the theta between quaternion 1 as the cosine inverse of Q0 dot Q1, right? So if you take the dot product and you get the cosine inverse, you get theta. Let's try to draw that just a touch nicer. So the theta between the two is that, and whatever our output theta that we want, right? So this is our theta 0, and our theta output is going to be theta 0 times t. So all we want to do is find, you know, maybe t is 0.5. Let's just, for example's sake, say that our t is 0.5, just so it draws nicely, right? So t is 0.5. That means that the actual theta that we want to find is, you know, let's try to get halfway between them, or reasonably close to halfway between them, right? That's about halfway, sure. Right? So this is our theta 1 here, right? Now, this Q0 is not, you know, your x-axis, right? Like, because remember, it's a 4D vector. It's not this, right? It doesn't matter what Q0 is, right? The rules of linear algebra apply regardless to whether this is defined as, you know, your standard. I think this is called standard basis, if it was the straight x-axis. I think that's called standard basis, but we don't care. We're not using standard basis. We're not, this exists in some plane arbitrarily floating in 4 dimensions that you can't possibly see, and one point of that plane is like, we'll call this 0 and 1, right? So we have point 0 and point 1. If we have this plane here, I'm drawing here, this is 0 and this is 1. So this plane is exactly chopped right through here. This is the origin. I'll write origin. All right, can we see? 0, 1, 0, 1. Stick it right through here. That plane is that. And this path along here is, like the path along the great circle is this path here, right? That's how it works in 3D. It works the exact same in 4D, but you can't visualize it. I can't visualize it. Maybe you can. But it's not important. All that matters is that the math is consistent between n dimensions. So, all we want to do then is find this quaternion here, right? We have Q0, we have Q1. We can easily figure out what theta we want. So all we have to do is find out what this quaternion is, which I'll just call capital Q, because why not? Well, how do we do that, right? Like this is actually pretty standard complex number analysis or Euler's formula. If you look up Euler's formula, Euler's formula. So if you look up Euler's formula, you get this little bitch here, right? It's actually not Euler's formula. Well, it is. Whatever. It's kind of not. It kind of is. Pretend I didn't say Euler's formula because that introduces complex numbers and we don't even need to think about complex numbers. All we want to do basically is get two basis vectors which we can then define a number on the plane with, right? And we're going to use our first input vector as the first basis vector. And then if we can find this basis vector here, we'll call this Q n because it'll be normal to this. If we can get this basis vector here, then we can figure out what this number here is, right? And it's relatively easy to get this basis vector, right? We want in addition to having just this basis vector, we want a thing called an orthonormal basis. And orthonormal just means it's orthogonal to all the other basis vectors and it's normalized, meaning it has a unit length 1, right? So if Q0 is one basis vector and Qn is the other basis vector, then Q0 dot Qn should be 0 and the length of Qn should be 1. Right? If this is satisfied, then we have what are called orthonormal bases. Both of these vectors are going to be on the plane, and therefore any linear interpolation on the plane of around theta will give us the point on the hypersphere that's between two quaternions. Does that make sense? We don't even need cross product. That's just way too advanced. It's also not defined in 4 dimensions, but you know. It's defined in 7 dimensions, though. Go figure. So how do we get Qn, right? This is pretty straightforward linear algebra. I'll do it here. So if we take, if we just project, you'll have to forgive me, I don't remember the syntax. I think this is correct. If we project Q1 onto Q0, I don't know. I never use, who fucking cares? Q0 dot Q1 times Q0. Right? So what that gives us, if we take Q0 dot Q1, we get some scalar, and its length is going to be whatever length this is. And we multiply it by Q1, we get this vector. Right? So we'll call this A. Right? So we now have A. Shit, that looks like a Q. So we have, fuck. So that gives us A, right? If we take Q1 and we subtract A from it, let's get a different color here. Let's get some yellow action here, right? Let's call this B. B is equal to Q1 minus A. And what does that give us? Well, that gives us this vector here, right? And if we draw it at standard position, we have this, right? That's A. Well, if we just A is equal to A over the length of A, we get, well, hold on. Let's do something super cool here. Let's just make this Qn. So we go Qn is equal to A over the length of A. We have our fucking orthonormal basis. That's it. That's all there is to it, right? So now we have Q0 and we have Qn and we have a theta. Now, who fucking cares is actually the mathematical formula for finding some of my life achievements? Yeah, pretty much. So we have an orthonormal basis Q0. We have two basis vectors that are orthonormal to each other, Q0 and Qn, right? So if we want to find our output Q, Let's draw it in white, because white contrasts well with black. Our output Q is just our cosine of the theta, and we've theta 1, right? That's this theta 1 here, which is just the input theta multiplied by t, which is the percentage between the two vectors. Cosine theta 1 Q0 plus sine theta 1 Q1. That's it. That's slurp. That really complex, crazy, four-dimensional, complex number shit that everybody talks about being super complicated or whatever, that's it. That's all there is to it. It's not complicated. It's very simple. All it is straightforward linear algebra, and what makes it complicated is people who don't understand how to work with linear algebra outside of coordinate systems explaining it. I think, at least. When I first learned this, the thing that I found really difficult was wrapping my head around what the fuck people were talking about, because no one was talking about it, what it actually was. They were drawing, like, I'm pretty sure if you go to Wikipedia, Quaternion slurp, I'm pretty sure if you go here, you're going to get, oh, that's actually not so bad. Yeah, here, so you're going to get this nonsense, right? Well, okay, it's actually quite simple. Alright, I give up. Yeah, okay, this is the nonsense that you get. You get this crap. You see this shit? What the fuck is this, right? Like, this is what you get when you look up slurp on the internet, right? You get this junk, and makes no fucking sense, right? If you can make sense of this, good for you. But I can't make sense. Like, what the... Who cares about this, right? Like, this is just a pain in the ass to work with, right? Like, no one cares about any of this shit. This isn't so bad. But anyways, yeah, really, right? Like, who cares? This seems pretty reasonable. But anyways, that's all that slurp is. All it is you find the plane. You have the plane because you have two quaternions. Any two 4D vectors that are not collinear define a plane. So you have a plane. The great arc around the circle is your interpolation, is your shortest distance between 2 points along your 4D circle. Your plane, all those points also exist on the plane. Then all you have to do is orthonormalize two basis vectors, find your input, which is just t, or find your output theta, which is just t times your input theta, get your orthonormal vector basis, and then you do Euler's little formula here to get your output quaternion. This is some sort of a trigonometry identity or something. There's something triggish in here, but I don't really know anything about formal stuff, right? What the fuck is this, an array of quadratic forms? I don't know. I don't know what it was, and I don't want to know what that is. All I know is this is all slurp is. Is everybody comfortable with slurp now? Does anybody have any problems with the idea of slurp and how it works and all of that stuff? Did everybody find that reasonably straightforward? Like cherry slurp. Yeah, cherry slurp's good. Is everybody cool with slurp now? Could everybody go and write a slurp function? Quite clear. Good, good. Okay. So we're all happy with slurp? Okay. Okay. So, how about now? Everybody good with slurp now? This isn't so true. This probably was true 10 years ago when this Jonathan Blow and Casey were all about not using slurp like 10 years ago. It's not so true anymore. Computers are fast enough that you don't really need to worry about the computation of slurp. I'm going to keep it here anyway. Computers are so fast that you don't really need to worry about using the computation of slurp, but there is a fundamental problem with slurp. So when you're trying to blend quaternions, you have three parameters by which you're trying to blend them, right? Your first parameter is, I think the term is commutative. I'm sorry, I'm really bad at formal math. That's where, like, ax plus b... Wait, ax... What does it mean? It's like ax... Oh, wait. ABC is equal to... Yeah, ABC is equal to BCA is equal to CAB... Whatever. It means that, like, the order... Yeah, that's what it means. Is that what commutative means? Commutative? I don't know. Like I said, I don't know formal math at all. Like, even a little bit. Slurp is basically slope in 4D. No. Slurp is basically rotation around a circle in 2D. Yeah. Commutative. That's the... Yeah, commutative? Oh, it's commutative. Oh, well, commutative. I told you, I don't know shit about formal math. So, commutative. Okay. Shouldn't learn anything from me. Commutative, okay. So that's one property that's desirable when rotating, when interpolating between slurp, is that property. Another property is a thing called torque minimal. Torque minimal. And I don't want to get into what torque I don't want to get into what torque is, but you can imagine if you have this great arc, if this great arc is the smallest distance between these 2 points, that's torque minimal. If your great arc did something ridiculous like this, where it wasn't the shortest distance across the hypersphere, or across the sphere, or across anything, that would not be torque minimal. That would be random. And then your third property is constant velocity. Okay, so you have, these are the three properties. Matrix multiplication. Matrix multiplication can be in certain situations. Right, so these are your three properties that you have to... These are your three desirable properties when choosing a method for blending between quaternions, right? You want all three of these, right? Unfortunately, this is not possible. As far as we know, mathematics has not gotten us to the point where you can have all three of these, right? You can have two of them. And depending on which two you want, you have to pick a method, right? The three methods that I know about, at least with regards to mapping things onto four-dimensional surfaces, the three methods that I know about are slurp, nlerp, which is just normalized lerp, and for the Handmade Hero people out there, Casey made this famous, or made this viable, so you can thank him. And the other is called an exponent map, and I don't know shit about them, so I'm not going to talk about them, because I'll say wrong stuff, and I don't want to sound like an idiot. Everything I've said is probably wrong, but yeah. Okay, so commutative, that's the word, commutative. Slurp, nope. Nlerp, yep. Torque minimal, yep. Nope. Constant velocity, yep. Nope. Yep. Pick two. You don't have it. You can't get all three, right? So, so if you have torque minimal and constant velocity, so torque minimal and constant velocity, right? Well, the problem is, so for slurp, that gives you torque minimal and constant velocity. If you have two rotations, if you only have two rotations, use slurp. Slurp is fine. When Jonathan Blow and Casey went on the anti-slurp tirade of 12 or 13 years ago at this point, It was because both you couldn't blend more than one animation, and also because Slurp's kind of inefficient. You have to take a bunch of arc cosines and you have to take a sine, a cosine, and an arc cos, right? I think that's all you have to take. But you have to take quite a few operations, right? And that's really slow. But like nowadays, computers are so fucking fast. Who cares? So if you have 2 rotations, Slurp is fine. But if you have like 6 rotations that you're blending from, you simply cannot use Slurp. Because like if you look at like any animation system, right? So if you have an animation system, right, you might have like you'll have weights and a quaternion. Weight and a quaternion. Weight and a quaternion. So let's say you have 3, right? And a quaternion, right? So if you have 3 quaternions and the sum, let's see if I can sum weight. Yeah, right. Like I'm going to use proper mathematical notation. I can't even remember where the fucking start point and end point go. The sum of your weight 0 plus weight 1 is equal to 1. I have actually written, using Granny Source, I have written dual quaternion blending for skinning. So I can talk about that if you want. After I do this, I can talk about dual quaternion skinning if you want. I have written that. It's okay. I'm not sold on it. But anyways, so if all your weights are equal to 1, this is a common thing that you're going to do in animation blending, right? If you have 4 quaternions, you simply cannot slurp them, right? Because if your animation program ordered them Q2, Q1, Q0, Q3, and it did like slurp these 2, and then slurp these 2, and then slurp this whole thing, right? Like this type of a thing, you're going to get a different result than if if these were reversed, or if it did like slurp these 2 and then slurp this and then slurp this. Like once you start dealing with more than 2 quaternions, slurp is broken. It's not well defined at all. So what Casey, and I believe he's the first to do it, he doesn't think he is, but I'm going to give him credit. What he figured out is you just fucking do this shit. You just wait. You got like a big Q at the end of that, and then you just fucking normalize it. And then you're done. And this is called normalized lerp. It's the dumbest fucking thing possible. It's just straight up add up your quaternions and then normalize them, right? So even if you don't have weights, right? Let's look at the difference between slurp and lerp here, right? So let's go back to our previous example here. Right? Whoa, okay, simmer down. Straight line time. So, we said this was Q0 and whatever, this is Q1, right? So if you slurp, you're going around the outside of a sphere, right? Basically what lerping does, like, so let's say this is your Q, this is your output Q here, okay? What lerping does is it just goes, like, barrels through the hypersphere just as you would barrel through a circle, right? So imagine that this is just on a circle. It just barrels through the circle, and you get maybe this vector, which is a little bit off, and then you just push it out, and then you're back on the circle, right? So when I said before that, I said that you don't get constant velocity, what that basically means is with your nlerp, 50% of the way, well, 50% of the way through is correct. 25% of the way through, so if you're lerping, let's say you're lerping exactly from 0 to pi over 2. Come on, Shawn, you can do, fuck off. There we go. So let's say you're lerping, you're going here, right? Your slurp is going to get you exactly here. It's going to be dead on. You're going to get exactly constant velocity, right? You're going to be moving the exact same amount correctly, right? For a normalized lerp, you're going to basically take this vector path. You're going to take this path at 25%. Maybe that's here, for example. And then you're going to push yourself back out. That's the normalization part of it here. So you're going to be off by a little tiny bit, right? The actual amount that you're off is incredibly small. Like, it's really, really small. And it doesn't matter, right? There's also, people have done spline fitting algorithms where you take slurp, or sorry, if slurp is defined as Q0, Q1, T, you do an nlerp of Q0, Q1, and then like some sort of a T where F is some sort of a curve function that basically, if you map 1t f of t. So if you just do a linear lerp, you get that. But if you do, I forget what the curve looks like. It looks something like this. Let's see if we can exaggerate it a little bit. At 0.5, your lerp is going to be correct, but at anything else in between, your lerp is going to be a little bit off. And the point at which it's off is halfway between 0.5, so eighth pi, and then multiples of eighth pi. That is where you're going to be off the most. But if you get a curve function that fits this reasonably well, you can get nlerp to look really, 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 really close to slurp, and you can benefit from the property where you can take 100 different quaternions, blend them all together, add them all up, and then normalize that shit, and you're really, really close to your slurp function, which you can't even do if you have multiple quaternion blending. Does all that make sense? That one makes the most intuitive sense, IMO, but I feel like you'd lose a bit of information when you renormalize. You do, that's right, you do lose a little bit of information when you renormalize. Like, you're a little bit off, but the amount that you're off is just, it doesn't matter. If you have like a camera that's like, it's hard to draw, it's hard to, if you're just doing this is just an axis. It doesn't include the rotation. So I'm going to try deodorant. So if you have like a rotation that looks like this, and then you blend it to a rotation that looks like this or whatever, like, the amount that your nlerp is off is really, really small, and it usually doesn't matter. If you're doing like a flight sim or any sort of a simulation, maybe it matters then. But if you're only blending between two quaternions, just go ahead and use slurp. It's fine. And if you're not blending between two quaternions, you're probably doing something with character animation, where your animation track has 15 keyframes or whatever, and you're blending between each of those. Who cares, right? Like, you don't even know what your animation program did, right? Your animation program could have done something completely different than what you're going to have in the game. So it doesn't really matter whether your nlerp matches up with slurp exactly, because your animation program probably didn't use slurp either. So it doesn't matter at that point. I didn't expect to actually learn something new about quaternions watching this, but I did. Thanks. Good. I'm glad you were able to watch something. Now, the other thing that I'm not going to talk about, because it's already gone on for about an hour and 15 minutes, and I said I wanted to keep it around an hour, is a thing called Quaternion double cover. And basically what Quaternion double cover does is it uses the property of quaternions that because we take theta over 2, a quaternion actually represents 2 full rotations around something. And it uses that property to determine which way, like if you have an arm, let me see if I can fucking draw. God damn it, I said I wasn't going to do this. That's a dude, right? So if you have the guy and his arm is like up here, I'd have to draw it in 3D. I'm not doing it. Basically, if you have an arm that's impossible, if you have a joint that's impossible to move, but the shortest path through that point is actually through an impossible way, normally you'd have to do like angular constraints, and you'd have to do a whole bunch of difficult, complicated, brittle algorithms. Like you've ever seen, there's a pretty famous GIF file of famous, but there's a pretty common GIF file. I've seen it many times on the internet. It's like a WWE referee, and he like does a thumbs up or something like that, and his head spins around, and his arm is all broken or whatever. All of that shit is those like weird sort of like impossible rotations are usually due to broken angular constraints on interpolated animations. What Quaternion double cover does is it uses, like when you author an animation for something, there's a rest pose, like it's a generic pose. Sometimes it's a T pose where your arms are like this, or sometimes it's a rest pose where it's just like the most natural position for you to rest. And basically it figures out whether you're in 360-degree rotation of the rest pose or not, and it makes sure that it never jumps 360 degrees past where you are in the rest pose, so that you always take the shortest path possible. And it's this technique called where IK breaks. I mean, yeah, I'm not gonna look at these videos, but yes, basically that stuff is really, that stuff, you see it all the time, right? And most of the time it's due to broken angular constraints. What Casey figured out 10, 12 years ago is that you can use the rest pose for a comparison function, basically, to determine whether or not what the actual shortest path is, right? Because you might have a shortest path, like if you have a rotation and you're considering it just on 360 degrees, you might be here and you want to get here, and like clearly this is shorter, like this is much shorter than going all the way around. But if this actually implies that you'd have to do all of this because you're using 2 rotations, then this way is clearly shorter. And you can figure this out just with a dot product with the same quaternion. It's not the dot product with the quaternion. Well, yeah, the dot product with the quaternion versus the rest pose. You can figure out whether or not you need to go this way or all the way around, right? You'll never ever want to go all the way around, so you can figure out that using comparing yourself to the rest pose. And there's a thing called double cover, and I don't want to explain it because there's nothing that I will say that Casey didn't already say. So what I'm going to do is mollyrocket.com quaternion double cover and the rest pose neighborhood. Where's my mouse? If you go here, there. I said this was going to be an introduction to quaternions, so I don't want to cover advanced topics like this. I'm not going to like do in-depth stuff about dual quaternion skinning either, for the exact same reason. If you want me to teach you dual quaternion skinning, let me know. I'll do it in another video. This was supposed to be an introduction. But yeah, if you're doing animations using quaternions, then you probably, like character animation using quaternions, you probably do want to learn about double cover. I have nothing to add that he didn't already say. His video didn't have an introduction to quaternions. His video only had the double cover thing, so I figured it would be good to augment that with an introduction to quaternions. So I have nothing left that I was going to say about all this. If anybody has questions, please let me know. I'll gladly answer them. I hope It seems like people seem to get some sort of an intuition or understanding of quaternions and slurp and what they are that maybe they didn't have before. So that's good. I feel pretty good about that. Did anybody find anything confusing? I can try to explain anything if anybody's struggling with anything. I know there's stream lag, so I'll wait. You have a bunch of questions. Yeah, please, go ahead, ask. Whatever those questions are. I will gladly answer as much as I can. If you have like formal math questions, you don't even bother. I don't know anything about formal math, but like, you know, man, I didn't even know what the fuck this word was. Like, come on. I'm really tempted to draw a penis while I wait for questions to be asked. Does a quaternion define an object camera rotation in the same way that a V3 defines a position, or do I also need to track my forward and up vectors? How do I answer this? Okay, so a quaternion doesn't define a position like a V3 defines a position, right? A quaternion defines a mapping of your axis and your angle onto a 4D circle, or hypersphere they're called, right? So a quaternion isn't a position. It is a position, but you don't treat it like a position. You treat it just like a mapping of your axis and your angle, right? So let's use your example of I am showing it. It's on YouTube, or it will be on YouTube tonight or tomorrow. If you follow me on Twitter, I'll post the link to it. So for a camera, I'm going to use your camera example, right? So let's say this is our camera lens. Right? That's a camera. Holy shit, I did it. It's on a tripod. I guess there's some perspective. Okay. So this is your camera, right? You're saying that you have a forward vector, which I assume is this, and you're saying that you have an up vector, which I assume is this. Right? Is that correct? This is how you sort of normally define a camera. This is a way of defining a camera as a forward vector and an up vector. So your quaternion basically defines all of this essentially, right? Let's see. How does it define it? Basically, I'm probably going to word this incorrectly. Like I have it in my head how I want to say it, but I don't think it's very good. But basically, what you're actually defining with your quaternion is an axis of rotation and an amount of rotation, right? So you could treat it as your axis of rotation is whatever your forward vector is, and your rotation is something like that, right? So your up vector in this case would be, you would need another vector, like a left vector, because you would need an orientation vector. So if you were to take the forward vector cross product with like a left vector, you could get an up vector, and then if you so that gives you that, and then your rotation around that would basically be your up vector, right? So this is going to be your up vector, and then you can rotate your up vector around your forward vector by some sort of a theta, and that's how you would get your axis and your angle, right? I don't ever do this anymore. I did like 10 years ago, but now all I do for camera rotation or camera orientation is a position. I don't touch that has nothing to do with its orientation. So position has nothing to do with this. And then all you're given is a quaternion, which is an axis about its rotation, and then how much it rotates, right? And that's how you would go to this. You would need a left vector as well, because you could cross product it, up vector, and then rotate around your forward vector. Does that make sense? Because you need a third vector, right? So you need like a left vector, a forward vector, and then your up vector, and then your forward cross your left gives you your up, and then you want to rotate your up by some theta. You want to rotate up by theta around forward, which would mean that your quaternion would be your forward vector sine theta over 2 cosine theta over 2. Does that make sense? No question, but I have looked at 3-4 things about quaternions in the past, and it was still gibberish. This is hands down the best explanation I've gotten, and the only time I've ever seen anyone explain it intuitively. Thanks a bundle. Wow, good. I'm really glad. Thank you. Good. Maybe I'll do more math lectures. Because I sort of, like, I went and I looked at all of the, like, I was like, what are quaternions? Let's see what people are saying. And I don't understand what the fuck they're talking about. And I feel like I understand quaternions. So I was really confused by what other people were talking about. So I get the impression that people who are talking about quaternions are the people who use them in Unity once and don't really understand them. But that's me. Did that explanation of the camera analogy help? I hope that's correct. I haven't really done that. So what's the procedure then for updating my camera? For translation, I can take my vector 3. Oh. Oh, so you want to update your camera orientation. So you have to turn your quaternion, like, in... It's like any linear algebra. I don't remember the formula off the top of my head. I can look up the code for it. I'll do that now, so you can see it. I don't remember how to do it exactly, but I could probably derive it, but I'll make an arithmetic error, so I'm not going to. Basically, like any linear transformation, I'm just trying to think of quaternions in terms of eigenvalues, but I don't want to get into that. Any linear transformation, when you do linear algebra, you generally use, or you always use a matrix, right? So any rotation matrix, or I guess it's a matrix of rotation. For 3 dimensions, it's going to be, you're going to have to turn your quaternion into a 3-dimensional rotation matrix in order to do that. I could painstakingly figure out what that rotation matrix is for you right now, but I will make errors. Thankfully, Quat 2 Mat 3. Thankfully, I wrote code to do it. And that's how you do it. So, XX, XY, XZ, XW. 1 minus 2F. This would take me all day to figure this out, to like recreate this, because I would fuck it up so badly. So basically, you turn your quaternion. There's code. I'll paste this somewhere. Oh wait, here's how I did it. I stole this code from somebody else. Let's see. Here you go. So you take your quaternion, you turn it into a matrix, and then you multiply your matrix by whichever vector you want to rotate, and that's how you do basically any linear transformation. The analog, yeah, for quaternion rotation is that. I have an interview Friday. It's going to be mathy. I suspect quaternions will be on there. I'll be rewatching the VOD. Slurp made sense even though I started watching halfway through. Cool. Yeah, I have a real huge problem with mathematicians. I sort of, like, as a hobby, read, like, things about particle physics. And particle physicists use very, like, even, like, really dense research papers by particle physicists are pretty clear. They don't use artificially inflated, difficult language. Everything is quite simple and quite manageable for me. But as soon as I get to a math paper, it's just like they're trying to... I get the impression that mathematicians want to speak only to other mathematicians, not to anybody else. And I just can't even be bothered trying to read half the fucking papers. Like... Stop making up symbols. Just fucking define what your symbols mean. Like, I've read so many papers where they've used some sort of a symbol that's been used a million times elsewhere for something completely different and then didn't define it. It's just like, please stop doing that. Like, I really, really dislike mathematicians. There was actually a really... There was an article. What was her name? Piper Heron? Piper Heron? Was that her name? Piper Heron. So Piper Heron wrote her PhD thesis. This is her PhD thesis. And I've gotten about halfway through it, and it's fucking great. It's actually like a human could read it, and it's funny. And I think I read a little bit about her because I started reading this, and I was like, hey, I can understand this. And I get the impression that she thinks this... Maybe I'm putting words in her mouth, I don't know, but I think she thinks that mathematicians are like that as well, like just make things complicated for no reason. You see it in social sciences all the time because they're trying to justify the fact that they're not a real field of study. Oh boy, I pissed some people off. And so they try to use these big words, and I feel like mathematicians do it too, and I wish they fucking wouldn't. But what are you going to do? I think if you decide on some initial, you can rotate those by the quaternion. Yeah. I don't know, like, yeah. Would it be better to convert quaternions to 4x4 matrices? It depends. If you want to pass them as matrices, like, you probably want to do it on the CPU, because if you do it on the GPU, you're going to do it, like, if you do it in, like, a geometry shader, you're doing it for every primitive. If you're doing it in the vertex shader, which is really likely, you're doing it for every single vertex. Like, if you have a model with 50,000 vertices, right, you're going to convert your quaternion to a matrix 50,000 times. I don't care how much faster your GPU is than your CPU at this sort of thing. Doing it once on the CPU is going to be much better than doing it 50,000 times on the GPU. And if it's your camera matrix, you're doing it for every single vertex. So if you're doing it in a vertex shader, you're looking at, you know, a couple 100,000 times you're doing it versus one. Number file. I do really like number file. The problem I have with Brady Heron's videos, and I think his videos are fucking excellent. I think he does a wonderful job. 60 symbols, number file, and periodic videos I think are great, but the problem is Did they try to explain really complex topics in 10 minutes or 5-10 minutes? And like sometimes you need to sit there for a few hours, or if you really want to understand something, a few weeks with something, or months even. And while he does a really like fantastic pop view of complex scientific and mathematical things, it doesn't really lead to anything that's substantial in terms of learning. So I watch them, I like them, but I have some problems with them. That's my same quat to math code I'm using pretty much. My issue is taking the controller input and figuring out the Quaternion rotation to increment the orientation. Okay. Is Quaternion rotation different from tracking forward? Yeah. Roll, pitch, and yaw. Roll, pitch, and yaw are Euler angles. That's the problem with that is if you start using Euler angles, it's really difficult to blend animations or blend two rotations, right? If you have just Euler angles, linearly blending them so that they're actually smooth is really impossible. If you're just doing like blending on one axis or whatever, it's fine. But if you're trying to blend three axes, like if you have 3 rotational degrees of freedom, you don't want to be using roll, yaw, and pitch. You're much better off just sticking with Quaternion and operating on it like how I showed. Faster Quaternion vector multiplication. Okay. Oops. Hey. What do we got here? Oh. Come on, Casey, what are you doing? What? Well, I don't... Maybe this works. He's saying that Fabian wrote it. So if Fabian wrote it, I'm going to say that it's definitely correct. But I mean, I haven't checked it. Maybe it works. I don't know. Like it doesn't really matter. But yeah, you can try this. I mean, they say that Fabian wrote it, and I say if Fabian wrote something, it's probably correct. You might not have to convert to matrices. Like, it's very rare that you're going to be operating just on a just on a vector time, like you want to rotate a single vector around a quaternion. That usually doesn't happen. What you usually want to do is build up a composite 4D matrix, send that to a GPU, and then have that just run through a bunch of shit. And if you just want to rotate a single vector around a quaternion, I guess this works just fine. Never used it. And yeah, I mean, they say Fabian wrote it, and if Fabian wrote something, it's probably correct. So I'm going to actually code this tonight or tomorrow and just give it a try. I'm sure it'll work. V prime QW. I'm not even going to pretend that I understand why that works without really thinking about it. Skinning and rotating bones in the GPU. What about it? What about skinning and rotating bones in the GPU? If you're skinning and rotating bones on the GPU, you're doing it with matrices. That's very likely. Like you're not sending raw quaternions to the GPU. You're almost certainly using. If you're just rotating, but you're not, right? Because you have a displacement from the bone, so you're gonna be in a 4D homogeneous vector. Maya, does Maya do that with GPU? I have absolutely no idea. If you're doing dual quaternion skinning, that's totally different. And yes, you can do that on the GPU. Maya does dual quaternion skinning now? I didn't know that. That sounds like a reason for me to use dual quaternion skinning then. Just because it matches Maya better. I already wrote it, so it's not like it's hard for me to use it. But I don't know, it's something I'll have to look into. I'm not convinced it's a good idea yet. What do I have? Maya 2016. Yeah, okay. That's what I got. Are there any other questions regarding whatever the fuck I talked about today? Slurp. It's probably the thing that is most misrepresented on the internets. You could, like, I was gonna get the Quaternion test, but the problem is that it uses all my libraries that I'm not quite ready to release yet. So I was gonna just do just give you the source code, but it's probably completely useless to anybody. Like, this is C, but I don't think it really looks like C to most people. So I can give you the source code, but you're not going to be able to do much with it, unfortunately. I don't think much of it makes sense. Alright, I am going to end this then. That was about an hour and 45 minutes or so, including answering questions at the end, which is good. Thanks, I'm glad everybody enjoyed the explanation. If you tweet at me what math you want to learn next, or what math, I think what's good is doing something that is like I said, I don't know much about formal math, but things that come up in 3D game programming and like 2D game or whatever game programming in general, I know a fair bit about, and I don't know the formal reasons why things are the way they are, but I know like I have an intuitive sense for more or less all of it. So anything but signal processing, I can probably do a reasonable explanation of. I don't understand. My New Year's resolution, other than to finish the third book of the Feynman Lectures on Physics, is to really understand Fourier analysis. Like get a real intuitive understanding of that and sort of signal processing in general, because I find it breaks my brain. So if you want to learn anything other than signal processing, let me know, and I will gladly do a comparable stream to tonight's. Any good sites for learning 3D game programming? No, there aren't. There are 0 good resources for learning 3D game programming. There's Handmade Hero, which will teach you everything about game programming, but nothing about 3D. And you should learn how to do 2D before you do 3D anyway. And Other than that, no, there was absolutely zero good resources for learning anything, which is why I decided to do some math lectures, because even Khan Academy, and I've went through and I've watched some Khan Academy lectures, they're not very good at teaching an intuitive understanding of concepts in a way that are applicable to real world situations, like game programming situations or real world situations. They're a good resource, I guess, if you're trying to pass your math class. Maybe, I don't even know. But I don't think they're particularly useful, unfortunately. Sample the signal, it's imaginary sine waves and get the frequency. Yeah, sure, it's about as much as I understand. Alright, I'm out then. Thanks guys for watching. I'll put this up on YouTube tonight, and I'll link it on my Twitter. So if you follow me on Twitter, it's SSS McGrath on Twitter. I'll post a link to this, and tweet at me if you want me to teach anything else about math or any programming. Like if you want to learn how, I don't fucking know, whatever you want to learn about programming, like some sort of weird, anything game related, like if you want to learn, like, I don't know anything. I don't know any formal terms for anything, right? I don't know any of that shit. But if you want to learn something, I probably, if it's to do with game programming, there's a high chance that I know it and can probably explain it. So if you want to learn anything, I really enjoy doing these teaching streams. I probably won't do them like weekly, maybe every 2 or 3 weeks. Entity component systems. Watch my streams, my actual programming streams, because I do entity component systems like this, and I have macros like this. And what I do is I stick everything in a union, and I call it a hacky discriminated union, and I use these macros here to get macro types, and I use auto, which is a C++ thing. It's the only thing that I really am so glad that modern C++ has, because I don't have to type these. I mean, it would be better if C++ wasn't a retarded language, but because it is, and then I use these macros with the paste operator to say, give me a bomb, and if it's a bomb, I deal with the bomb, and then this memory here sits exactly on top of the memory everywhere else, and then I have a giant array of entities. So I don't use entity component systems, and they're not runtime, they are compile time. I don't use entity component systems. I stick everything in a hacky discriminated union, which I don't think I've ever seen anyone do before. So that's my take on entity component systems. And I'm working on entity stuff right now in the game. So if you want to learn about entity component systems, or how I do them, which is not how most people do them, you should watch my streams. I'm streaming every day at 1 p.m. Eastern Time, every day, for 4 hours straight. So if you want to learn about that sort of shit, you should watch my programming. All right, I'm out. I'll probably stick around. I'll stick around on chat for a little bit if anybody has any questions, but I need to use the washroom and get a beverage, so I'll answer questions. I did networking stuff first. I did networking stuff on day one. Before I did anything else, I did networking stuff. No, they're not components. Like, there's no components. I just copy and paste. Like, the spread shot has a damage factor. Well, whatever. So does this one. Who gives a fuck? Right? Like, I just say what the thing needs, right? This one has a damage too, and it doesn't even overlap with this damage. And you know how much it matters? It doesn't. You might bitch that oh, it's going to take as large as the largest one, but like in this case, the largest one's going to be a player. I could just take the player and shove it into its own thing anyway, or take all of the player stuff out, like camera pos and client ID. I could take all of this shit out, shove it in somewhere else later, and then make all the entities roughly the same size, and I won't even worry about wasting a ton of space, right? This is going to waste quite a bit of space just because the player's like quite a bit larger than all the other entities, but for the most part, all the entities other than the player are going to be roughly the same size. So what I'm going to do later is take all of the stuff specific to the player out. I'm going to compress all the entities to roughly the same size, and then I don't have to worry about anything. You don't have to do any of that stupid shit. Entity component systems are dumb. I don't know. Maybe they're smart. I've never found that to be a good way of doing things. That's just me. Alright, I'm getting out of here.